So now let's take a look at question 1. Use symmetry to evaluate the following definite integrals. So start with this, question 1a. Whenever we see something like the symmetry, we need to think of the even functions and odd function. And the function here is apparently a even function. That is because when you input the negative x, the output is the same when you input the x, right? So you can see that this it's even because when you input negative x, the output you get is the same when you input x. Right. Okay, so knowing that, we can use the symmetry. So this is the interval is also a symmetric, so now this becomes twice of this definite integral from 0 to 2 absolute value of x, the square root dx. And the advantage of using the symmetry is because we will be able to simplify the function that's being integrated, because now we know that the upper bound and lower bound, they're both greater than 0. So we know that in this situation, x is greater than 0. When x is greater than 0, we can remove the absolute value with no cost. So this is has become x when x is greater than or equal to 0. Okay, since x is from 0 to 2, I can now change this, just remove the absolute value here, and now it becomes x. Okay, so now I'm solving this definite integral, and apparently I will need substitution. And now I'm gonna let this x go into the differential sign. Going into the differential sign, I mean I need to integrate this x, right? That is, how we work with the differential sign. Whenever you take something out of the differential sign, the thing becomes the derivative of itself. So let me demonstrate here. So for example, if you have x3, right? You want to take this x3 out of the differential sign, then you're going to take the derivative, which is 3x squared dx. Right? And the thing I'm doing is, the other way around. When I want to, take this thing, put this thing into the differential sign, then it becomes the integral of this thing, which is, the integral of 3x squared, it's x to the 3, so it becomes x dx to the 3, right? So it's the reverse operation. So what I'm doing here is this thing. Okay, so now twice of this, square root of x squared plus 1 d 1 over 2 x squared, right? And now I see that there's a 1 over 2 inside the differential sign, which can be cancelled with the 2 outside of this differential sign. That is because what the differential sign is doing is essentially taking the derivative. And we know that when we take the derivative, we can factor out the constant before we take the derivative. So you can just factor out this 1 over 2 from the differential sign, and it's kind of going out, right? And then cancel with the 2 there. So now I have this left, dx squared, right? And now the next step, I'm gonna change this dx squared to dx squared plus 1. That is because I have x squared plus 1 inside my square root, and I want to create something that is the same as that thing so that I can let u equal to x squared afterward to do my substitution. So if you're confused about that, I will explain. This thing is the same as dx squared. That is because, like I said, what the differential sign does here is it takes the derivative of the expression inside the bracket. And we know that taking the derivative of 1 is 0. So it does not matter if you add constant to the bracket. So this is just like the derivative of x squared is the same as the derivative of x squared plus 1. That is what this thing means here. Now, I can let u equal to x squared plus 1, since the thing inside my differential sign is the same as the expression inside the square root, right? And by letting u equal to x squared plus 1, I can do the substitution, and in the same time I also need to change the upper bound and lower bound accordingly, right? So this becomes now square root of u, right, du, since x squared plus 1 has been replaced with u. And now the lower bound 0, right? I'm gonna plug in 0 into this expression here, x squared plus 1. So 0 squared plus 1, that is 1. So my new lower bound, it's 1. Okay? And my new upper bound can be obtained by plugging in 2 into x, this expression here. So 2 squared plus 1, that is 5. So my new upper bound is 5. Now, after this step, it's gonna be very easy, right? You can just use the fundamental theorem. Maybe just look up to your formula sheet. This is 1/5 u to the 3 over 2 du, right? Which is equal to that is, what is that? That is this 2 over 3 u to the 3 over 2 5 1. Oh, I made a mistake here. Is 1 over 2, no, 3 over 2. Here is 1 over 2. Okay, and then to plug in and do the computation, that is 3 over 2, right? U to the 5 to the 3 over 2 minus 1 to the 3 over 2, which is 3 over 2 times this 5 to the 3 over 2, that is 5 to the 3 square root minus 1, and this can be simplified to 5, square root of 5, right, minus 1. Okay, so that is the final answer. If you don't like this expression, simplify it further, but that's not a big deal. And the point here is how we use the even function, the property of the even function, and how we do the substitution. Okay, so that is our question A, right? Dealing with the absolute value. Now let's take a look at question B. Now we're gonna use symmetry, right? And then it's easy to see that this is a odd function. That is because usually when you get something that is very complicated and it's also not on the formula sheet, and also you have some symmetric interval, and then it's very likely that this is gonna be a odd function because the answer is gonna be 0. So after doing lots of exercises, you will have this kind of experience. So let me convince you now this is indeed a odd function. So that is when you plug in negative x, the output is the opposite, right? So this is odd because when you input negative x, the thing you get is the same as the thing when you input x. The opposite. It's the opposite of the thing that when you input x. There's no negative sign here. We can check this very easily. So it's a odd function, and because the interval is also symmetric, so this is equal to 0. Right. Of course, we also need to mention that the function is continuous, right? Which is kind of obvious. This function has to be continuous on the interval -5 to 5. Because the domain is all the real numbers, right? And can also mention this for the previous question, which I forgot to mention. Just continuous on this interval. Okay, so the question B is a lot easier than the question A, because for all function there's nothing we need to do. It's just equal to 0. Okay, so that is our question B. Now let's take a look at question 2. Let f of x equal to this. Find this definite integral. This is also a very easy question. Usually when the expression is super complicated, the question turns out to be easy, because it just wants you to apply some magical theorem. So we're gonna find this definite integral. So we will think of the fundamental theorem of calculus. The fundamental theorem of calculus tells us that we can find the definite integral by finding the original function. So suppose you have the original function, then you can just plug in the upper bound into the original function minus the thing you get by plugging in the lower bound. So now we've known that the original function of this derivative f prime of x is the f of x itself. Right, so this is the original function. So by the fundamental theorem of calculus, we can just do this. F prime x dx is equal to f of x is 1, 0, right? But before doing that, we have to mention that this satisfies the condition of the fundamental theorem of calculus, FTC. The condition of the fundamental theorem of calculus requires that the function that is being integrated is continuous. How do we know it is continuous? Well, you can take the derivative of this function to verify that, but let me just briefly mention the idea, right? Firstly, you notice that the domain of this f of x includes the interval 0, 1. So what I'm saying is, firstly, this 0, 1, this interval, it's inside the domain of f of x. Because for whatever value from 0 to 1, when you plug into the original function, you will always get a valid output, right? The denominator is not going to be 0, right, unless x is equal to -2. And this expression inside the log function is always greater than 0, right? You can just rewrite this as, factor out the e squared, then is 1 minus x plus x, right? X is from 0 to 1, so this expression 1 minus x is going to be greater than 0, and x is also going to be greater than 0, so this whole expression is going to be greater than 0 when x is inside the interval from 0 to 1, right? So this is inside the domain. And then this thing applies, right, to the derivative. Because the derivative can be obtained by using the product rule and the chain rule. And those functions you produce will be some kind of composition of these type of functions. So they will have the same domain as this function. That is complicated to explain, but should be easy to understand. If you're not convinced, you can just take the derivative, go through these steps, and you will see that those things that you're getting is made of sign of some kind of this expression, right, and this log function, and the only condition that you need to check is the expression inside the log function is greater than 0, and also denominator not being 0. So it has the same condition. So we say that this 0, 1 is inside the domain, right? So therefore this thing, it's continuous on this interval. But again, anyway, the purpose of this question is not testing you to do the derivative, and instead it wants you to just make use of the fundamental theorem of calculus. So you shouldn't be too concerned about proving that the function f prime of x is continuous on the interval 0, 1. It's okay to just briefly mention this thing to indicate that you have noticed this condition. Okay, so now moving on, we can plug in. Okay, so plug in 1 and plug in 0, right? Plug in 1, so we have sine of pi, okay, e to the 1 divided by 1 plus 2 ln e squared plus 1 times 1 minus e squared, right? This thing minus, plug in 0, right? Pi times e to the 0, 0 plus 2 ln e squared plus 0 times 1 minus e squared, right? So it's easy to understand. And then it simplifies to negative 2. That is because, in this expression here, you cancel out the e squared, and this term is actually ln1, right? This is ln1. ln1 is equal to 0, right? So the first term can be ignored, and for the second term here, that is sine e times e to the pi times e to the 0. Sine pi is also 0. Sine pi. And not actually sine pi. It's, so the second term, it's sine pi over 2, which is 1, right? And this thing, when you cancel out, after you cancel out this, it's gonna be ln e squared, which is 2, right? So it's negative 2. So that is our question 2. And now let's move on to the question 3. Use substitution to evaluate the following indefinite integral. So for this type of question, we're gonna play the same game about going out and in into the differential sign. So notice that in the bottom we have x cubed, so we want to create the x cubed in the differential sign so that we can do the substitution. So the first try is to put this into the differential sign. Okay, so it becomes the integration of this x squared, which is now 1 over 3x cubed. Okay, and as I said, I can move this 1 over 3 out of this differential sign. So 1 over 3 comes here. And then I can also change the expression in the bottom. Just flip it, so it becomes x3 minus 1 to the 4, right? Because the 4 is an even power, I can just swap the signs, and it doesn't hurt me to do that. And now I'm gonna change this dx3 to dx3 minus 1. Because the derivative of dx3 is the same as the derivative of x3 minus 1. Now I have the expression in my differential sign, same as the expression in the denominator, which is kind of easy to manipulate. So now I can let u equal to x cubed minus 1, right? So this now equal to 1 over 3, 1 over, this is u to the 4, right? This is du. And then moving on, this is u to the negative 4 du, right? And then we can just apply the formula. So it becomes u to the negative 3, right? So it's a 1 over negative 3, right? U to the negative 3 plus c. Right. And now I will need to substitute the u back into this expression. So it becomes this negative 1 over 9 x cubed minus 1 to the negative 3, right? So that is 1 over this cube, right? Plus c. This is the final answer. Okay, so that is our question 3a by using the substitution. Now let's take a look at question B. Use substitution, right? So we have x4, right? And the idea to create this x4, x to the 4, it's obviously by integrating the x cube. So it's very natural to think of letting this to go into the differential sign, right? So that is integrating this expression. So I have this left here. Then after going into this differential sign, this x cubed minus x becomes d of x to the 4. Actually is 1 over 4x to the 4, right, minus 1 over 2x squared, right? Now I can factor out the 1 over 4 from the differential sign, so that I can have factor out the maybe write one more step so that is not too confusing. So this is d. I factor out the 1 over 4, right? And I'm left with x to the 4 minus 2x squared, right? And I continue to factor out this 1 over 4 out here. So it now becomes 1 over 4, this sine of x to the 4 minus 2x squared, d of this same thing, right? So now it's natural to think of viewing this x to the 4 minus 2x squared as a whole thing. So now we will let u equal to x to the 4 minus 2x squared as my substitution, right? And now this is equal to 1 over 4 sorry 1 over 4 this sine of u, right, du, right? And now we can just look up the formula. It's easy to figure out. This is negative cos u, right, plus c, okay? And I also need to substitute the expression u back into here. So it's gonna be negative 1 over 4 cos of this x to the 4 minus 2x squared plus c. Should not be too difficult to understand, right? So the confusing things here is the ugly expression, a complicated expression, x 4 minus 2x squared. But it's easier to think of letting that to go into the square root and do the also the obvious factorization. Okay, so that is our question B. All right. Now let's move on to question C. Question C here. If we want to let this go into the square root, you see that it doesn't help. It creates the x squared, right? But our expression that is being integrated is 2 minus 3x to the 9. So you see that this trick does not work here. So now we need to let the complicated expression to be u. So this 2 minus 3x equal to u. Okay? And now we're gonna turn this into u to the 9, and in the same time I need to express the x in terms of u. So solving for x, we have x equal to u plus u minus 2, right? U minus 2 divided by negative 3, right? And also we need to deal with the dx, right? And so take the derivative. Dx is gonna be negative 3, 1 over 3 du. Right. Now plug in everything into this expression. So now I have x replaced with 1 over negative 3. There's u minus 2. And then the original ugly expression, it simply becomes u to the 9. And dx now is replaced with negative 1 over 3 du. Okay, just replacing everything. And then sort out things a little bit. So this becomes 1 over 9. Here, u minus 2 times u to the 9 du. Okay, so that is the expression sorted out. And we're gonna multiply through the bracket. So it becomes two terms. This is u to the 10 minus 2 u 9 du. Now it's just straightforward by the formula. Okay, the formula tells us that this is 1 over 11 u to the 11 minus 2 times 1 over 10 u to the 10, right? This is the original function, and then I plus c after. Okay, so that is the final answer. You can simplify this a bit if you want, but it's not a big deal here. So that is basically how we use the substitution in the other way for question C. Okay, so that is question C. Let's move on to question D. So question D here seems very complicated, and so the complicated thing here is the cotangent x minus pi, right? So we will try to let the u equal to the cotangent x minus pi, right? And then we take the derivative on both sides. So it becomes the du equal to the derivative of cotangent as the secant square, cosecant square, CSC square x dx, right? This is u, which is the same as the numerator there. So now we can see that by doing that, we can replace the dx with 1 over, we can replace this, let me just write this separately. So CSC square x, right, divided by cotangent x minus pi square dx. Now we can replace this part with the du, right? And then the denominator can be written as u squared, okay? So now this becomes 1 over u squared du, which is a lot simpler. And now I can write this as u minus 2 du, and by the formula it becomes 1 over just negative u to the negative 1, right, plus c. And then I can replace u with this expression, so it becomes negative u to the negative 1 is 1 over u, so it's 1 over cotangent x minus pi, right, plus c. So it seems very complicated, but actually it's not that complicated once you figure out the trick. And it's it doesn't hurt to try letting something equal to u. If it doesn't work, you try the other expression, and then this is always based on experience. The more you try, the better sense you have doing this stuff. Okay, so that is our question D. Now move on to the next question. They should be not so difficult. If you're comfortable with the question 3, you should be comfortable with question 4, because they are pretty much the same stuff except for plugging in the lower bound and upper bound. So for this expression, the 2x minus 1 inside the square root is difficult to work with, so we will try letting u will be equal to 2x minus 1. We need to solve for x, so x now becomes u minus 1 divided by 2, and dx now becomes that's 1 over 2 du. Okay, now I replace the expression. This becomes square root of u 1 over this, right? Dx is replaced with 1 over 2 du, and I need to change my upper bound and lower bound. Input the lower bound into the x here, right? So 2 times 1 minus 1, that is, input this here, right? Input this here. So you have the new lower bound, that's 2 times 1 minus 1, which is also 1 here. And the new upper bound, that is 10 minus 1 is 9, okay? So we have this thing here, and simplify a little bit, that is u to the negative 1 over 2 du. Okay, so now I plug in the formula. This becomes just u to the 1/2, and with the upper bound 9 and 1. And we can just plug in, right? Plug in, so it becomes 9 1/2 minus 1 1/2. That is 3 minus 1, which is 2. Right. So that is question A. So let's move on to the next question, question B. We have cosine x, sine x. So the trick to play with sine x, cos x is do the integration and the derivative. So one will become the other, right? So you have the exponent there, cos x plus 1 is easy to think of letting x go into this differential sign. So the sine of x becomes cos of x. Okay, so now I have this left outside the bracket, and when x go into the differential sign, it becomes negative of cos x. Okay, but we know that the sign does not matter because we can always factor out the sign. So factor out the sign, it becomes this 5 to the cos x plus 1 d cos of x. Still, it does not match the expression there. It has a plus 1, right? So we will plus 1 in the differential sign. Since the derivative of 1 is 0, it does not hurt to plus an arbitrary constant. So we plus 1 here. Now these expressions, they become the same thing, right? So I can just let my u equal to cos x plus 1, right? And now I replaced this with 5u du, and also need to replace my upper bound, lower bound. The new lower bound is cos 0 plus 1, which is 2. And my new upper bound is cos pi over 3 plus 1. That is, pi over 3 is 1/2. So that is 3/2. Okay? So with this, I apply the formula. That becomes negative. The integral of this, it's 1/ln 5 to the u, right? And with the upper bound 3/2 and lower bound 2, and the final answer is 25 minus 5 square root of 5 divided by ln 5. If you go through the computation, it's not so difficult to figure out, just like the question, which question? Question 1 or question 2, right? So that is how we handle the substitution. Okay, should be very obvious here. And now let's move on to question C. we have ln x, right? So to create this ln x, it's easy to think of integrating the reciprocal function 1 over x, because the derivative of ln x is 1 over x. So I will let this 1 over x, this thing here, go into the differential sign, right? And I have now this 1 over x disappear, and I have this left, right? And inside my differential sign I have d ln x. Technically, it will be ln absolute value of x, but since x is from e to e squared, the restriction of the lower bound and upper bound, so it's the same as writing just ln x. There's nothing different between ln absolute value of x and just simply ln x, right? Now we can view this ln of x as a whole thing, because in our expression the only thing that we have is ln x, right? So now we will let u equal to ln x, and now the whole expression can be written as u squared plus 3 times u du. Okay, and my upper bound, the new upper bound, it's ln e squared, so it's 2, right? And ln e is 1, right? So this thing, and then simplify the expression by expanding the bracket, so u3 minus plus 3u du, and now use the formula straightforward. It becomes 1 over 4 u to the 4, right, plus 3 over 2 u squared, and plug in the upper bound, lower bound, and skip the computation, and the final answer is 33 over 4. You have the final answer. Okay, so that is how we do this question by substitution. And you see there's, as before, nothing too much difficult. And the one thing maybe is difficult is how to observe that what kind of substitution you need to use, and that comes with experience and practice. So that's why we're doing lots of example here. And after practicing a lot, it will become just obvious to know which substitution you will need to use. Okay, that sounds very absurd, but it's genuinely true for this kind of exercises. So now question D, right? So in our expression we have a loss of e to the x, so it's natural to think of letting u equal to e to the x. Okay, now this becomes, of course we need to figure out the du, right? Du is equal to ex dx, right? So now I can factor out the ex on the top, so this becomes ex minus 1, right? Ex plus 1 dx, right? And now you can replace ex dx with du, or just simply ask this to go into the differential sign. So it becomes ex minus 1 ex plus 1 dex, right? Now it becomes u is ex, so u minus 1 u plus 1 du, right? And I also need to figure out my upper bound, lower bound. My new lower bound, it's e to the 0, which is 1. And my new upper bound is e to the 1, which is e. Okay, so figure out this. And the next step is to split this thing. So this u minus 1 divided by u plus 1 can be written as u plus 1 minus 2 divided by u plus 1, which is 1 minus u2 divided by u plus 1. Okay, so I replace this expression by 1 minus 2 divided by u plus 1. The reason of doing that is because we can get rid of the variable in the numerator, right? So now we can do just plug in the formula, right? So it becomes, this is u, right, minus, this is 2 times ln u plus 1, okay, with the upper bound e and lower bound 1. And then plug in your upper bound, lower bound. You have e minus 1, right, minus 2, this ln e plus 1 minus ln 1 plus 1. Okay, and then the final answer becomes just well, this is e minus 1 minus 2 ln of e plus 1 minus e 2 times ln 2. Or maybe we can combine that. Well, it's, you know, acceptable to give this form. If you don't like this form, you can you know, combine these two things here, right? So that can be written as e minus 1 minus 2 times ln e plus 1 divided by 2. Okay, so it's not again, not a big deal. Our point is not, you know, try to write this in a nice form. Our point is to do the substitution, is to do the integration. Okay, so that is question D.